So, today I would really like to talk about how we can solve the increasing need for quality AI, which is a word I've heard quite a lot since the beginning of this. So, the agenda for today is me talking a little bit about how I went from being a quantum physicist to have a really strong interest in hardware, shortly about what is quality AI, the increasing need for it, and then a potential solution for this problem, which is called the FPGA. I will talk more about that and how the FPGA addresses quality AI needs. A little bit about us and what we do, some use cases, and then a conclusion. So yeah, when I studied quantum physics, I was desperate for a student job, so I got a job at a bank as a customer consultant. And it was very random. I just needed some money. And we quickly realized while I was working there that I could probably help with some other things than customer consultancy. So I quickly started doing more optimization and automation of their internal processes. And I got more hungry. So I switched over to an insurance company where I looked more into their deeper algorithms where I was optimizing and automating that stuff. And I realized that I really like that field, but it's so outdated, the finance field. And I got more interested in how could AI actually solve some of these things because there are many manual tasks and I'm a little lazy. So I got very interested in natural language processing and switched my focus from quantum physics to computational physics so I could program more and dive into deep learning. So I focused a lot on natural language processing, got even more hungry, and then I got quite interested in high frequency trading. Not because it's morally correct, but it's very interesting how they do the things. And I remember I got to talk with some of these guys and asked them, well, can I do something for you? Found a company, and they told me that they had their AI models implemented. It was easy for them, but they had some limitation when it come to the efficiency and when it come to the energy. And they were like, well, if you want to have something to do for us, maybe you could look more into that. And I went back to my professor at University of Copenhagen and asked, well, how can I solve this problem? And then he recommended me to look more into the hardware. So I started Googling around and bumped into this FPGA chip, which looked horrible, but also interesting. And yeah, I started looking more into that and applied for a scholarship in the at UC Berkeley, where I could work at this as my master thesis, but also as an entrepreneurial idea. So that's what I did. And I was very interested in understanding um, other companies if they were struggling with the same kind of thing when it comes to efficiency and um, energy consumption. And I was very fortunate to be around Silicon Valley. So I talked from small drone companies to IBM and Google and Amazon. And what they all had in common was that I kept bumping into this word quality AI. And I kept asking, well, what do you mean with this quality AI? So what I concluded was that these were the things they were mentioning the most. So it was about the high performance of the algorithms. They want them to be efficient, optimize, and deliver accurate results. The other thing was the reliability. So consistently produce dependable outcomes, which is very fair. And something they were all talking about was this robustness, which is basically the resilient of the hardware that actually runs the algorithms, so it can handle different kind of environments, because they were struggling a lot when they had to run the algorithms through their hardware. It often died and they had to change it or switch it over again quite often, and this was quite a problem because it takes away the robustness and then it takes away the reliability and the high performance algorithms. And then an ethical part, which was the increased trust. So obviously you would like your algorithms to produce a reasonable outcome every time. And they were very talking a lot about this privacy of their data, and both when it came to internally, but also externally when it came to when you have something AI running out in the field, people running around that. You have to have some security to that when it comes to that. And I interviewed 100 different companies, and I think I boiled it down to what they were actually looking for was this reduced latency. Because basically, when you have reduced latency, you actually have something that runs efficiently enough. And privacy and security was also a big buzzword from all of these things. And so it made more sense the more I talked to different companies who actually mentioned these things. And also here I saw that the most used AI things were especially in the robotics process automation. And yeah, there's a big interest there, so I guess that's where they use it the most. But also, computer vision and NLP is also some of the most used AI solutions right now. And what I realized they all have in common that they have this kind of risk, high risk potential, especially when it comes to data they run, but also when it comes to, again, this the solution used out in the field. And I'm very interested in the solutions out in the field because that's where you have, more problems when it comes to external factors. So yeah, uh, then to dive a little more into the hardware that they actually use. So basically, the more that the AI evolution has been growing, well, the more computing power there's needed for. And basically, when they started looking into artificial intelligence, people were much more interested in the algorithms themselves. So understanding how can we make this do something, how can we make it solve a problem, and of course, the deeper you dive into the deep learning and the algorithms, the more you have to look into hardware actually being able to run your algorithms. And so this is where these names come from, and basically. To give you a short resume on the difference of these hardware. So the CPUs are, you can call the most flexible hardware, and they are quite used in a lot of areas. What they are really strong at is that you can easily program them, and they work in a sequential manner. So you go from A to B to C, which is nice. However, if you want more efficiency, you probably want to go further up this line. And this is where the GPU comes in the picture. GPUs are some of the most used hardware out there, and they are very, very strong when it comes to uh, graphic data. That's what they were made for. And also, they are really, really strong when it comes to training data. You would mostly want to use a GPU when you're training your AI algorithms. However, if you are looking for more efficiency when you have a specific task, then you want to go further up the line. And this is where the FPGA and ASIC come in. But the further up the line, the more customized the hardware is, which also means that they are not as flexible. So if you're really looking for a optimal efficiency and energy consumption, well, then you would probably go with the ASIC. However, we are in a time right now where AI is not fixed. That means that your AI gets updated often, or you need to change things, you need to retrain it, and then you probably don't want to use an ASIC. So this is where the FPGA could be maybe the golden thing in between right now. And this is what we are seeing. So many companies who actually deploy AI into their models, into their product, are getting more interested in moving further up this line. But embedded AI implementation is highly complex, and it's time consuming, and it is also quite expensive. And I had a professor working with me from Stanford, Professor Merman. He was a very strong FPGA enthusiast, and he told me that FPGAs are extremely useful and efficient, but painful to deploy. So, what is special about this chip is that it has three main features. It has parallelism, which means that instead of calculating A to B to C, you can calculate A, B, and C at the same time and therefore get a quicker answer. They are also known for giving low latency, and that's because you imagine them as blank canvas. So you basically design exactly how you want your architecture to look like, and therefore make sure that you have a specific task being done without other things affecting around. And then the last thing is that they are more energy efficient because of the architecture of the chip. So that's what they are known for. They are reprogrammable. But even though they are reprogrammable, that doesn't mean that it's an easy way to reprogram them. And this is why many are quite afraid of this chip, even though they have a quite strong interest. It's a love-hate relationship you have with this chip. Um, but they're really, really good if you have some specific customization that you are looking for to have. Is again, if it is the energy efficiency you're looking for, to say, for example, a drone. You know, drones right now can fly an average 30 minutes. You don't want something to eat up the the energy of that. Or if you have very strong latency requirements, for example, in high frequency trading, you would like to have real time solutions happening very fast. So people cannot really let go of this chip, and this is why we at the University of Copenhagen was researching about, well, how can we make this easier? Just to show you a little bit about how it works right now. So even though the chip has been existing for the last 50 years, the development cycle has not been updated that much for many years. It's still quite the same way people go about it. So just to give you an idea how it works, well, if you have an AI model, you want to translate it all the way down to the chip, but there are some few steps in between, and you can do it in various ways. You can directly code everything in Verilog or VHDL, which is a low-level language. However, it takes quite a lot of time. It's not that uh, I wouldn't say it's the most trivial language to use, and it's not because the compiling time is fast. So it's quite a heavy thing to sit directly with that. So people have been trying to move it a little further up, where they use where they design the architecture in higher languages, but that also takes quite a lot of time, because if you are a system architect, uh, your your AI model looks quite different in the hardware architecture in itself. And that actually is something many companies are struggling with, because the time for the development cycle and the demand is too slow compared to the work that needs to be done. So again, at the University of Copenhagen, we have been trying to look at, okay, how much can we take away and move up further up? And this is where we then decided to make Cheetah AI. So basically, what we focus on is to take the translation part, where you actually design the hardware architecture for your specific needs, done through our platform. And that also means that you very quickly can get something that you can test and verify. And this is basically what many companies are struggling with, because let's say you test and verify, well, you want to redo it again and test it again, and that time can become quite big. So that's why we take that away from you. You can choose different optimization, if it's the energy you're looking for, if it's the memory, if it's the compression of the model, that if you have very little space in a hearing device, then you can choose that, and we will design an architecture that makes sure that works. So what we have realized throughout these conversation is that to use FPGAs and AI, it's often require that you understand AI and hardware. And that's very hard for an engineer, because we only get taught, at least here I know, in one of the things. So to have engineers who understand both is quite a problem. So therefore, the platform is built around that. You don't have to have prior hardware knowledge, and can actually focus on the optimization of your model. Then obviously we are very interested in minimizing the latency, and since you can replace a few engineers, you also minimize your cost. And for us, one of the main focus is the time to market, because something we were seeing a lot of companies were struggling with is that many of them died as a company because they could not deliver the product very fast. So this is a main focus for us, that you get a fast time to market from months to a few hours. Shortly about the team. So basically, I started this while I was in the US, and my postdoc, who was my co-supervisor, has been with me from the beginning. He also wrote his PhD in this field, also using what I've been researching about. Then I have 2 business developer and a third FPGA AI engineer. And I would say what we as a technical team have in common is actually the understanding of hardware and AI, and therefore actually being able to build this platform. And also we have been building a framework where we take all of the lower level hardware design part and build it in so we use C++, but using energy right now on automating the process, so it doesn't need to be done manually. Behind me as advisors, I have a guy from DTU, Martin, who is the FPGA teacher here. And we have been talking a lot about this problem, actually to that degree that he has been looking for making a new course where people actually get taught in AI and FPGAs, because we are seeing a really big demand in the market for these kind of people. And I have my professor, James Avery, who is working very closely with us, as you can see, and then my professor from Berkeley, Conrad, who is helping us on the business side. A little more about the use cases that we are solving right now. So I did mine for this high frequency trading, and this is when I got a little more blood on my tooth. Can you say that in English? Maybe. So basically, what was very interesting for me and made me quite interested in this was that I actually managed to deploy this onto an FPGA and make their algorithm 121 times faster. So what they offered me after that, and that's actually why I started the company, was, well, we can get a job, but if you want the job, we have to own everything you did. And that's when I realized, okay, maybe this is actually useful for someone else. And what is also special about this chip is that we can decrease the energy used, which is a really, really big problem nowadays with the climate changes going on, right? I mean, servers and hardwares are a really big sinner, so people are very interested in this. Then Carl in his PhD also managed to, so this was onto a CPU, but using the same kind of framework on the hardware architecture design, and managed to also make the post-processing run from 200 milliseconds to 15 milliseconds, and we optimized the pre-processing algorithm to become 42 times faster. And right now we are working with a trash sorting company who has the same kind of problem. So they are building these small cameras they're selling to where they use computer vision to sort trash. And their problem is that their algorithm is not running efficiently enough. So they are looking for an FPGA to maybe make that run faster. We are talking to a lot of drone companies, especially in the agri-tech field, because obviously, if you have any dynamic things you need to detect quickly, you have to work in real time. And they also have strict requirements when it comes to the energy and also to compression of the hardware into the drone, because there's actually not that much space in them. We are talking to, who more? Drone, trash sorting, food sorting, supply chain management is our third one. Robotics is also quite interesting. And then there are smaller autonomous vehicles who are also very interested in this. So this is the different fields we are looking into. Quickly, conclusion. So basically, to answer the things we talked about, so quality AI in its core is privacy and efficiency. The increasing need for quality is pushing the requirement, but also the time to market. The FPGA is a strong solution because of its parallelism, low latency, and energy efficiency. However, the AI deployment into the FPGA has a slow development cycle. And this is where we come in. We are here to move the development cycle from 6 months to a few hours. And one of the main reasons for us is to give SMEs a chance to join AI innovation because, yeah, as a small company ourselves, we would love to see others also succeed. So I hope that you are interested in joining our vision to become the big next AI enabler. And if you are interested in helping, we are actually looking to expand our team. So if you have any of these experiences, please reach out. Or if you know anyone who could be a good fit, you're also very welcome to engage with us, with me. If you use your phone over that spot, you can always contact me. And also, if you know any VCs you think could be a good match for us, please send them our way. Thank you so much.
Thank you so much, Amira. That was super duper interesting. Do we have any questions in the room? If not, I'll open the floor. You had one? Go for it.
Thank you. Thank you, Amira. Great talk. So the question I have is about the NPU, actually. When you talk about the CPU, GPU, and FPGA and ASICs, then where is the NPU, basically? Can you elaborate a little bit?
There's also a VPU.
GPU, of course.
GPU. Yeah, I guess why I mentioned these is, well, first of all, just to give a broad explanation of the hardware, and also more looking into the most commonly used hardware. So, I mean, there are a lot of PUs out there, and they are good for different kind of things. But when it comes to this specific task, when it comes to handling specific AI tasks, that are consistent and frequent, then it made more sense for me to put in the FPGA and the ASIC, and also because the NPU is just also a CPU, but with different kind of tasks in it. So I thought I just wanted to give a broader explanation.
I agree. So basically, the NPU is closer to CPU on that figure that you show,
Exactly.
basically.
Exactly.
Thank you so much.
Thank you.
Any other questions?
It was regarding the accessibility for SMVs, or SMEs, it's called in English. But how do you effectuate that strategy?
You mean targeting SMEs?
Yeah. How do you manage your?
Yeah, good question. Yeah, well, our pilot customers right now are small, medium-sized companies, and so how we are doing it is inside sales using our network and the conferences we join to connect with those companies, because that's the ones we want to target right now. So most of the portfolio companies we have in our target list we're talking to are actually medium-sized companies.
Yeah. Do you combine a soft funding strategy with that? Because there's a lot of some soft funding means for that specific target group.
You mean in terms of how we charge them? Yeah, okay. Yeah. Well, obviously we have to charge something so we can survive ourselves. This is basically taking a lot of the work of your own people. So hopefully this is also, we see this as an important add-on to your company. So how we do it is that they see that they can replace basically an engineer with us, and we give at this stage some discount because that's where we're at, right? So it's also very important for us that the companies we find actually have a very specific need, and not that they want this because it's cool, but they actually are struggling with it. And if you're struggling with it, you obviously also want to pay for it. And that is how we go about it. Yeah.
So how might one of the SMEs out there listening right now, how might they know that they're an ideal candidate for working with you?
question. Well, if you have any specific requirements, as mentioned earlier, when it comes to latency, you need something really to run in real time, or you have problems with your energy efficiency that you cannot optimize it enough, or as mentioned, you want to compress it down to a small device. I think this could be a quite good solution for you, especially if you are struggling with having the right resources, and that's also meant as people, because many companies are struggling with finding these talents. So if you would rather just have a solution than having the talents, the very specific talents, then I think this could be an interesting solution for you. And I mean, you're always welcome to reach out to me and we can have a talk. It's not bigger than that. Yes.
Thank you. Christine, do you have any questions online? Okay. You have one?
Hi, thank you for the talk. I mean, this is a problem. I have a few colleagues trying to program FPGAs, and they absolutely hate it. So it's good to know that someone's doing something much more high level on this topic. I was wondering, so FPGAs are very commonly used to build ASICs quite often. And I'm just wondering, is there some way, if you start having problems that crop up quite often, to actually transition to a solid chip?
Yes, definitely. That's a very good question. So yes, FPGAs were in the beginning made for testing before you deployed it onto ASICs, as mentioned. However, one thing we have been seeing is the growth and evolution of the FPGAs. So nowadays, the FPGAs are becoming quite strong, and that means that they can actually almost compete to a degree with ASICs. And they're also getting cheaper, which was one of the bigger problems before. So because of these things happening for the FPGAs, people are actually leaning a little more towards using these. And just to give you a little number, FPGAs are actually cheaper up until 400,000 units than if you use an ASIC. So if you use less than 400,000 units, maybe an FPGA could be a solution for you, but it's true back in the day, and still to this day, it is used to being tested on and trained for. But with this increasing need for quick demand and quick solutions, FPGAs are actually getting their comeback right now in the market, it looks like. I mean, we are seeing that Xilinx, who is the biggest chip manufacturer of FPGAs, got acquired for $35 billion 2 years ago. So we can see that there is growing interest in this specific chip. So I think actually that that's not maybe the case as much anymore. They can actually have other use cases.
Thank you.
Thank you so much. I think that's all the questions we're going to have time for right now. Let's give her a warm hand.